right, our next presenter this morning is Ella Hort, who's joined us from Pomona College. Ella's been working with Allison this summer, and she'll tell us about their project together, characterizing faint radio galaxies through their optical spectra.
Thank you so much, Gwen. Thank you all for being here, and let's get started. So first of all, what are faint radio galaxies, and why should you care about them at all? In essence, they're pretty much exactly what their name sounds like. They're just galaxies that are faint in radio wavelengths. And there's generally two main reasons that radio emission is produced in a galaxy, and those are from active galactic nuclei and star formation. Generally, faint radio galaxies are very interesting because they were only newly observed. So until recently, there wasn't the technology to observe them at these faint wavelengths. But now with new technology like the Very Large Array, they can be observed. So by looking at their spectra, we can characterize a population that we know very little about as a scientific community. Additionally, radio emission in galaxies is very interesting because radio emission from star formation, as opposed to from an active galactic nuclei, is a dust unbiased tracer of star formation rate of a galaxy. And by using star formation rate of galaxies at various redshifts, we can actually work to trace the star formation history of the universe and draw conclusions about how our universe came to be as we see it today. So in that way, it can really be used to answer some of the most fundamental questions of astronomy at this moment in time. So what characteristics can we determine from looking at these optical spectra? There's really four main ones, and those are star formation rate, so whether the galaxy is star forming and active or dormant, information about its type, so whether it's elliptical, spiral, or irregular, whether it contains an active galactic nuclei or not, as well as information about its redshift and its distance from us. With that framework in mind, my guiding research questions this summer were: what information can be learned about galaxies by examining their optical spectra? Are these galaxies radio faint because they lack significant star formation or AGNs? Are they faint simply because they're so far away from us? Is the answer actually somewhere in between those two options? How can we learn more about faint radio galaxies in general, and how does this knowledge contribute to our greater scientific picture of the universe? In this way, this project was really exploratory, and it was mostly just interested in exploring an object that we know very little about. The first chunk of my summer consisted of determining which galaxies were worth examining. We started with a radio table from Cosmos. So we had galaxies and then their radio flux values. And from there, we worked to determine which were the faintest, which we did by calculating the bottom 25%. We found that cutoff to be at 16.3 microjanskis. So our bottom quarter of the faintest were sources with flux values below that. For a little bit of reference about how faint those are, when we think of radio galaxies, we generally think of ones with active galactic nuclei in them, which often have radio flux values of several thousand. So in comparison, these are quite faint. Once we determined that bottom 25%, we checked that catalog against the Cosmos Demos catalog in order to find sources that were present in both. From there, we ended up with about 280 sources present in both catalogs, about 80 of which we ended up throwing out due to lack of confidence in their values. And so at the end of the day, we had about 200 galaxies present in both Cosmos Demos and our radio catalog, all with radio flux values below 16.3 microjanskis, spanning across various redshifts all the way up to around 5. Once we'd done that, we were ready to actually start using the spectra data from Cosmos Demos to begin making spectral plots and analyzing them. We did this analysis mainly in two ways: through visual analysis and cross-correlation. Visual analysis, which was just to make the spectral plots, use the smoothing process to clean them up, and then visually identify trends from there and draw conclusions. This was very useful for many of our sources. For ones that it wasn't useful for, cross-correlation was necessary, which was comparison to spectral templates to draw conclusions for that. This is an example of a source that visual analysis was useful for. So here we have the gray in the background is the raw, unsmoothed observed spectrum, and the blue is the smooth version. The smoothing process basically just attempts to reduce noise and makes the trends more visually evident. And this is one that has some clear trends going on. So as you can see, it has these two broad emission lines, and that's something that's really only possible of happening when there's an AGN. So this is a galaxy that just from doing the smoothing process and looking at the plot, we can say with some confidence that there's most likely an AGN in this galaxy. This is another source where that was useful for. As you can see, it has that jump, and the location at which that jump is happening combined with the redshift value were provided leads to the conclusion that that's most likely a strong 4,000 angstrom break. And that's something that usually is indicative of an elliptical galaxy. So this is another one that we can smooth the plot, look at it, and then say there's most likely an elliptical galaxy, and we can characterize it just off that. This is a great example of what was the case for many of our sources, which were ones that even once we'd done the smoothing process, they really just looked like noise, and there were no trends that could be identified from that. And that's where cross-correlation really came into the picture and was absolutely necessary. Cross-correlation is basically a fancy way of multiplying two things against each other and seeing how well they overlap. And we did that by using the chi-squared test. The chi-squared test compares an observed to an expected and then spits out a number, and the number tells you how well the two align. So we did that by looking for the lowest chi-squared value, which indicated the better alignments. By running the chi-squared test for our sources against a variety of templates, we were able to sort each galaxy into more broader and specific categories and see how well they aligned with different types of galaxies. One of the first difficulties we ran into was the necessity to use different spectral templates for our low redshift sources versus our high redshift sources. We had more templates that were usable for low redshift. So for our sources with redshift values below 1.5, we had about 30 spectral templates, all from SDSS, that were usable. And this is an example of just 3 of them. So here's a spiral, an elliptical, and a galaxy with an AGN. But as you'll see in the result distribution, we had many types, and we had a pretty diverse assortment of galaxy types in our sample. For our high redshift sources, so for sources with redshift values above 1.5, our template choices were much more limited due to that redshift compatibility. And in our short amount of time we had, we only actually scratched up 4 to use quickly, which were all for quasi-stellar objects or quasars. So at the end of the day, we actually had a lot of issues with our high redshift sources, and any results we were able to get from that were not nearly as diverse or believable as our results for our low redshift sources. Aside from just generating a chi-squared value, we could also plot the raw observed spectrum and the smooth observed spectrum against the normalized and shifted best fit template spectrum. So here in the orange is the template spectrum that returned the lowest chi-squared value. This is an example of one that actually is a pretty good fit. It had a pretty low chi-squared value. And obviously, as you can see, it's not perfect. It doesn't line up exactly, but it does have those same trends happening, and those emission lines happening in the same place. And this is an example of a best fit template that was a star-forming galaxy. So this is one that from doing cross-correlation, we could determine what was going on in this galaxy, and it was something that we couldn't do just through visual analysis. This is an example of one that did work for our high redshift sources. This is that same source from before that I said from visual analysis most likely had an AGN. And happily, our best fit template was for a galaxy with an AGN. And this one is a worse match than the one before. As you can see, it does have those broad emission lines happening in the same place, but they're not quite the same height or strength. But of our high redshift sources, this was really one of the best matches that we found in terms of determinations there. Our result distribution, particularly for the low redshift sources, was very exciting and also very reasonable based on what we expected. So the majority of our galaxies, as you can see, were star forming, and we had the most of star forming 4. The different star forming types just correspond to different strengths and widths of the emission lines. So star forming 4, for example, has less H alpha emission than the other star forming types, which actually is a reasonable thing to have seen with these faint radio galaxies, because if these galaxies have a lot of dust in them, then their H alpha emission is probably getting dampened, but their radio flux values probably wouldn't be. But as you can see, we do have a lot of different types represented here. We have red, blue, green, spiral elliptical, all those. So we were able to categorize them pretty diversely and have a good sample there. Unfortunately, as I mentioned, this was not the case for our high redshift sources, and we were not able to get as good a distribution because we were only checking them against 4 templates, all of which were for quasars. For future pathways of continued research, the main thing to do would be to continue working with these spectra to make even more specific predictions, which could most likely be done by locating even more diverse and redshift compatible templates. And this is especially important for our high redshift sources. So if we could find better high redshift templates that represented more different types of galaxies, we would be able to get better results that we could feel more confident in and even lower chi-squared values. Additionally, another interesting thing to do would be to use models instead of actual spectral templates. This could be useful because in a lot of ways it would eliminate issues we were having with that redshift compatibility, as well as make some certainty in the fact that we would know exactly what was going on in the template that was being represented. In terms of implications, my work this summer really just helps to identify specific characteristics in our sample of faint radio galaxies and further characterize a population that we know very little about as a scientific community. So hopefully it helps to just answer some questions that the astronomy community has about faint radio galaxies. Thank you so much. Do you have any questions?
Questions for Ella?
Yeah, so I remember you mentioned making a cut of about 80 sources.
Mm-hmm.
Can you explain more about what characteristics you were looking at and like why did you like completely get rid of them?
Yeah, that's a great question. So when we ran that query on Cosmos Demos and it returned the 280 sources that were present in both our radio table and Cosmos Demos, it had a little index in one of the tables that I think was called the Q value, which basically just told us how confident they were in their results. And I think there was 0 to 2. So anything with a 0, basically they were saying that they did not have any real confidence in their results from that. So for things with 0, which there were about 80 of, I think we also cut ones of 0.5. We just threw out and decided we're probably not valuable sources to be checking.
Nice, nice work. My question is about how does this population of faint radio galaxies compare to other, like maybe which we could call more typical galaxies in terms of that kind of star formation, like the template distribution, like what you found for faint radio
like
galaxies?
how the distribution
Yeah.
compares? Oh gosh. Well, our distribution really depended in a lot of ways just on the sample we were looking at and also obviously the templates we were using. I don't know for sure how it compares to like regular galaxies, but I do know that compared to normal, what we would consider radio galaxies, usually they all have AGNs in them because that's where they're getting their radio flux values from. So it was very exciting that we saw that these faint ones were mostly star forming as opposed to AGN, because star forming radio emission is usually fainter than AGN radio emission. So this was actually a reasonable thing to see. So I do know how they compare to regular radio galaxies, but I don't know about normal galaxies, but that's a great question. I will look into that.
Great. Other questions for Ella?
So in your future work slide, you mentioned that you want to use models instead of actual spectral templates. So can you kind of explain what you mean by models? Like what kind of models are you using for this?
That's a great question. So mostly I think that would just entail using like basically synthetic templates. So as opposed to all of our templates we were using were for actual galaxies. So they were just the spectra of like real galaxies that existed that we'd identified characteristics in. Using models would just be using created spectra of fake galaxies basically, which sounds like it wouldn't be as useful, but can be great because we don't have to adjust for redshift in that case. And also we know exactly what's happening in those synthetic spectra. So we can say like, we know for sure that that fake galaxy that we've basically created has this happening in it. So it just eliminates a lot of the confusion there and could be helpful. So in that way, yeah, models would be great.
Great. Let's take Ella.